I'm so glad you found your way here. Your body is made of ancient stardust from dying stars, and tonight, you'll discover how massive objects can actually bend the fabric of reality itself. You'll discover how gravity warps the universe, and by the end, you'll understand why space and time are not what they seem. Welcome to 100 Sleepy Facts. Wherever you are right now, perhaps gazing up at the night sky or simply feeling Earth's gravity holding you safely, allow yourself to rest in this cosmic stillness. We'll drift through 100 space facts about black holes and space-time, from Einstein's revolutionary ideas about curved reality to spiral galaxies hiding supermassive mysteries, to the moment when space itself bends so deeply that nothing can escape. These quiet journeys through space create a cosmic community of peaceful minds. Feel free to like and subscribe or share a thought down in the comments. It helps others find their way here too. One sleepy soul at a time. It means the universe to us. Settle deeper into your pillows now. Let your shoulders drop, your breathing slow and steady. You don't need to hold on to any of this cosmic knowledge. Just feel that peaceful heaviness spreading through you, like you're floating weightless in the vast, silent darkness between stars, drifting gently toward sleep. Close your eyes and breathe deeply. You're floating where starlight paints pathways through infinite space. Let your mind drift with cosmic silence. And now we begin. Black holes are among the most mysterious objects in the universe, and they challenge everything we thought we knew about space and time. These cosmic phenomena are regions where gravity becomes so incredibly intense that nothing can escape once it crosses a certain boundary. Not light, not matter, not even information itself. Scientists first predicted their existence through mathematics long before we had any way to observe them directly. Albert Einstein's equations from 1915 suggested that massive objects could warp spacetime so severely that they'd create these gravitational traps. For decades, black holes remained theoretical curiosities, existing only in the abstract world of calculations and thought experiments. But as our telescopes improved and our understanding deepened, we began finding evidence that these impossible objects are not only real, they're everywhere, quietly shaping the cosmos in ways we're only beginning to understand. The term black hole wasn't always used to describe these objects. Physicist John Wheeler coined the phrase in 1967, but the concept existed long before that name stuck. Earlier, scientists called them frozen stars or collapsed stars, trying to capture the idea of stellar remnants compressed beyond recognition. Some even called them dark stars back in the 18th century, when scientists like John Michell first imagined stars so massive that light couldn't escape their gravity. The name black hole captured public imagination because it evoked something both simple and terrifying: a hole in space itself, a void that swallows everything. Yet, despite the dramatic name, black holes aren't really holes at all. They're objects, incredibly dense objects with mass and gravity. The darkness comes not from emptiness but from gravity so powerful that light itself cannot climb out. To understand how black holes bend space and time, we first need to understand what space and time actually are. Before Einstein, people thought of space as an empty stage where events unfold, and time as a universal clock ticking forward at the same rate everywhere. Space was just the distance between things, and time was simply duration. They seemed completely separate and independent. But Einstein's theory of relativity changed everything. He showed that space and time are woven together into a single fabric called spacetime. This fabric isn't rigid or empty. It's flexible, dynamic, and responsive to the presence of mass and energy. Massive objects create curves and dimples in this fabric, the way a bowling ball creates a dip when placed on a stretched rubber sheet. These curves are what we experience as gravity. Einstein didn't set out to discover black holes specifically. He was trying to understand gravity itself, to figure out why objects attract each other across empty space. Newton had described how gravity behaves. Objects pull on each other with a force related to their masses and the distance between them. But Newton never explained why this force exists, or how it travels instantly across vast distances. Einstein proposed something radical. Gravity isn't a force pulling objects together. Instead, massive objects bend the spacetime around them, and other objects simply follow the curves in that bent spacetime. A planet orbiting a star isn't being pulled by an invisible force. It's following the straightest possible path through curved space, like a marble rolling around the edge of a bowl. This idea that gravity is curved spacetime sounds abstract, but we experience it constantly. When you drop something, it falls not because Earth pulls it down, but because Earth's mass curves spacetime, and the object follows that curve. When you feel weight pressing you into your chair right now, that's your body resisting the natural curve of spacetime created by Earth's mass. You're not being pulled down. You're trying to follow your natural path through curved spacetime, but the chair pushes back, creating the sensation of weight. Every massive object in the universe creates these curves. The Sun curves spacetime around it, and Earth follows that curve in its orbit. Moons curve spacetime, stars curve it, galaxies curve it, and black holes, they curve spacetime more extremely than anything else in the cosmos. So, how do black holes form? They begin as ordinary stars, but stars with a special requirement. They need to be massive, typically at least 20 times the mass of our Sun. Stars spend most of their lives in a delicate balance. Nuclear fusion in their cores generates outward pressure from heat and light, while gravity pulls everything inward. For millions or billions of years, these two forces balance perfectly. But eventually, every star runs out of fuel. When a massive star exhausts its nuclear reserves, fusion stops. The outward pressure vanishes, and gravity wins decisively. The star's core collapses swiftly in a fraction of a second, compressing inward with quiet inevitability. The outer layers explode outward in a supernova, while the core continues collapsing inward, compressing matter into an impossibly small space. What happens during this collapse follows physics into realms we rarely encounter. Atoms, which are mostly empty space under normal conditions, get crushed together. Electrons get pushed into protons, creating neutrons. For a moment, the collapse might stop at a neutron star, an object about 12 miles across but containing more mass than the Sun, where matter is compressed to nuclear density. But if the collapsing core has enough mass, even neutron pressure can't stop the collapse. Gravity overwhelms everything. the matter continues compressing, past the point where atomic structure exists, past the point where nuclear forces can resist, past the point where matter has any structure at all. It compresses into a singularity, a point of infinite density where all the mass exists in zero space. A black hole is born. Black holes come in different sizes, each with its own story. Stellar mass black holes, formed from individual dying stars, contain roughly 5 to 100 times the Sun's mass. They're the most common type, scattered throughout galaxies wherever massive stars have lived and died. Then there are intermediate mass black holes, containing hundreds to thousands of solar masses. Scientists are still figuring out how these form, perhaps from collisions between stellar mass black holes or from the direct collapse of massive gas clouds. And finally, there are supermassive black holes, monsters containing millions or even billions of solar masses. These giants lurk at the centers of most large galaxies, including our own Milky Way. How they grew so enormous remains one of astronomy's deepest mysteries. The black hole at the center of our galaxy is called Sagittarius A star, pronounced Sagittarius A star. It contains about 4 million times the Sun's mass, all compressed into a region smaller than Mercury's orbit around the Sun. For years, scientists suspected it was there based on the motion of stars near the galactic center. Stars were orbiting something invisible, something with tremendous mass. By tracking these stellar orbits over decades, astronomers calculated the mass and position of this hidden object. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, not the black hole itself, but the glowing ring of hot gas swirling around it. This image confirmed what decades of observation had suggested. Our galaxy's heart contains a supermassive black hole. So, yes, black holes are already changing our understanding of space and time by existing at all. They prove that Einstein's equations describe reality accurately even in the most extreme conditions. They show us that space-time is not just a mathematical abstraction, but a physical thing that can be warped, stretched, and even torn. Before we detected black holes, some physicists wondered if nature had some unknown mechanism that would prevent their formation, if something would step in to prevent infinite density and infinite curvature. But nature has no such safety mechanism. Black holes exist. They form naturally when massive stars die, and their existence means that space and time can be bent far more severely than we once imagined possible. The question isn't whether they bend space-time, it's how. The boundary around a black hole is called the event horizon. This isn't a physical surface you could touch, but rather an invisible boundary in space marking the point of no return. Once anything, matter, light, information, crosses the event horizon, it cannot escape. The escape velocity beyond this point exceeds the speed of light, and since nothing can travel faster than light, nothing can get out. The size of the event horizon depends on the black hole's mass. For a stellar mass black hole of 10 solar masses, the event horizon has a radius of about 19 miles, forming a sphere roughly 38 miles across. For Sagittarius A star, the event horizon spans about 15 million miles, but regardless of size, the principle is the same. Cross this boundary, and there's no coming back. The event horizon gets its name from the concept that events occurring beyond it cannot affect or send signals to the outside universe. Imagine standing safely outside a black hole and watching a friend approach the event horizon. As they get closer to this boundary, something strange happens from your perspective. You see them moving slower and slower. Time itself appears to slow down for them. The light from their body gets red-shifted, stretched to longer and longer wavelengths, becoming dimmer and redder. Eventually, they seem to freeze just above the event horizon, their image fading to darkness. But from their own perspective, nothing special happens at the horizon. They cross it in finite time, experiencing no particular sensation at the boundary itself. This difference in perspective reveals something profound about spacetime near black holes. Time doesn't flow at the same rate everywhere. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. This effect, called gravitational time dilation, occurs everywhere gravity exists, but it's usually tiny. On Earth's surface, time runs slightly slower than it does on a mountaintop or in orbit, a difference measurable by atomic clocks but insignificant in daily life. Near a black hole, however, time dilation becomes extreme. Time slows dramatically as you approach the event horizon, and at the horizon itself, time effectively stops from the perspective of a distant observer. Space and time bend together, inseparably linked in this dance of gravity. Light itself behaves strangely near black holes. Light always travels in straight lines through space, but when space itself is curved, those straight lines curve too. Near a black hole, light paths bend dramatically. Photons that would normally travel in one direction get deflected by the intense gravitational field. This effect, called gravitational lensing, causes black holes to act like cosmic magnifying glasses. Light from stars or galaxies behind a black hole bends around it, creating multiple distorted images or bright rings. The Event Horizon Telescope images of black holes show this effect beautifully. Bright rings of light from the accretion disk, bent and distorted by spacetime curvature. These images capture light that has traveled along impossibly curved paths through warped space. The mathematics describing spacetime around a black hole is called the Schwarzschild metric, developed by Carl Schwarzschild in 1916, just months after Einstein published his field equations. Schwarzschild found an exact solution to Einstein's equations for the spacetime around a non-rotating, spherically symmetric mass. His solution revealed the existence of a critical radius, now called the Schwarzschild radius, where spacetime curvature becomes infinite and time appears to stop. Below this radius, the roles of space and time actually swap. Outside the event horizon, you can choose where to move in space, but time marches forward inevitably. Inside the event horizon, you can move freely in time's direction, but all paths in space lead inexorably to the singularity at the center. Space and time exchange their properties completely. Most black holes don't sit in empty space. They're surrounded by swirling disks of gas, dust, and sometimes torn-apart stars. This material, called an accretion disk, spirals inward toward the event horizon, heating up through friction and compression. As matter in the accretion disk accelerates to incredible speeds, sometimes approaching the speed of light. It reaches temperatures of millions or even billions of degrees. At these temperatures, the disk glows brilliantly in X-rays and other high-energy radiation. This is how we detect many black holes, not by seeing the black hole itself, which emits no light, but by observing the extremely bright radiation from material falling toward it. The darkest objects in the universe create some of the brightest phenomena in the cosmos. Some black holes don't just pull matter in, they blast it out in powerful jets. These jets, extending thousands or millions of light years into space, shoot out from the regions near the black hole's poles at nearly the speed of light. Scientists think these jets form from a combination of the black hole's spin and magnetic fields threading through the accretion disk. Material spiraling inward gets caught in these magnetic fields and channeled along the rotation axis, accelerating to relativistic speeds and escaping before crossing the event horizon. These jets can outshine entire galaxies, pumping enormous amounts of energy into the surrounding space. They demonstrate that while nothing escapes from inside the event horizon, the region just outside can be extraordinarily energetic and dynamic. Recent observations from the James Webb Space Telescope have revealed black holes in the early universe, existing less than 1 billion years after the Big Bang. These discoveries puzzle astronomers because these black holes are already surprisingly massive, containing millions or billions of solar masses. How did they grow so large so quickly? Traditional models suggested black holes would need billions of years to accumulate such mass. But here they are, fully formed cosmic giants in what should be the universe's infancy. Some scientists propose these early black holes formed directly from the collapse of massive primordial gas clouds rather than from dying stars. Others suggest they grew rapidly through intense periods of matter consumption. These early black holes are reshaping our understanding of cosmic evolution. Black holes aren't perfect vacuums that consume everything nearby. There's a common misconception that black holes act like cosmic vacuum cleaners, sucking up everything around them. In reality, black holes only capture material that comes too close or that has insufficient angular momentum to maintain a stable orbit. If you replaced the Sun with a black hole of equal mass, Earth would continue orbiting normally. Our orbit depends on the Sun's mass and distance, not on whether that mass is a bright star or a black hole. The danger comes only when something approaches close enough to the event horizon. At safe distances, a black hole's gravity behaves just like any other massive object. It's proximity that makes them deadly. Gravitational waves offer another way to detect black holes, particularly when they collide. Einstein predicted that accelerating masses should create ripples in spacetime itself, waves that propagate outward at the speed of light. But these waves are incredibly faint, requiring cosmic scale events to produce detectable signals. In 2015, the LIGO Observatory detected gravitational waves for the first time, coming from two black holes spiraling into each other 1.3 billion light-years away. As they merged, they released more energy in gravitational waves than all the stars in the observable universe were emitting as light at that moment. This detection opened a new way to observe the universe, not through light, but through the vibrations of spacetime itself. When two black holes orbit each other, they create a binary system that gradually loses energy by emitting gravitational waves, This causes the orbit to slowly shrink over millions or billions of years. As the black holes get closer, they orbit faster, emitting stronger gravitational waves and losing energy more rapidly. Eventually, they enter a death spiral, orbiting hundreds or thousands of times per second in the final moments before merging. The gravitational waves from this final dance carry information about the black hole's masses, spins, and orbital dynamics. By detecting these waves, scientists can effectively hear black holes colliding across the universe, measuring cosmic events that produce no light whatsoever. Space-time itself becomes our messenger from these violent mergers. The singularity at a black hole's center is where our understanding breaks down. According to Einstein's equations, all the black hole's mass compresses into an infinitely small point with infinite density. But infinity appearing in physics usually signals that our theories have reached their limits. Most physicists believe the singularity represents a place where general relativity no longer applies, where quantum mechanics must somehow merge with gravity. But we don't yet have a complete theory of quantum gravity that can describe what actually happens there. The singularity remains hidden behind the event horizon, unreachable and unobservable from outside. Perhaps this is nature's way of hiding its confusion, placing the breakdown of our understanding safely behind a cosmic censorship barrier. Stephen Hawking changed our understanding of black holes by showing they're not entirely black. Using quantum mechanics, Hawking demonstrated in 1974 that black holes should emit faint radiation due to quantum effects near the event horizon. Virtual particle pairs constantly pop into existence throughout space. Normally, these pairs annihilate each other almost instantly. But near an event horizon, one particle can fall into the black hole while the other escapes. To an outside observer, this looks like the black hole is emitting radiation, now called Hawking radiation. This radiation is incredibly faint for stellar mass or larger black holes, far too weak to detect with current technology. But over astronomical timescales, it means black holes slowly evaporate, gradually losing mass until they eventually disappear completely. The evaporation of black holes creates a puzzle known as the information paradox. Quantum mechanics insists that information cannot be destroyed. If you know the complete quantum state of a system now, you should be able to determine its past and future states completely. But when a black hole evaporates away through Hawking radiation, what happens to all the information about everything that fell in? Does it disappear, violating quantum mechanics? Or is it somehow encoded in the radiation, preserved in ways we don't yet understand? This paradox has driven decades of theoretical work, with physicists proposing various solutions involving quantum entanglement, holography, and radical new views of spacetime itself. The answer may require a complete theory of quantum gravity. These observations and discoveries reveal that spacetime near black holes behaves in ways that challenge our everyday intuition. Time slows down, space curves dramatically, light bends along impossible paths, matter and energy transform into pure gravity. Quantum mechanics and relativity dance at the edge of the event horizon. And yet, despite these extreme conditions, black holes exist throughout the universe, formed naturally from dying stars and ancient cosmic collapse. They're not science fiction or mathematical curiosities, they're real objects that we can observe, measure, and study. So, yes, black holes bend space and time by creating such extreme mass concentration that space-time curves back on itself, forming boundaries called event horizons. The question that brought us here is beginning to reveal its answer layer by layer. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronauts we send to the heavens, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. To truly understand how black holes bend space-time, we need to visualize what curved space actually means. Imagine space-time as a flexible fabric, like a stretched rubber sheet. When you place a massive object on this sheet, it creates a depression, a dimple in the fabric. Smaller objects nearby will naturally roll toward this depression, following the curves in the sheet. This is essentially how gravity works. The sun creates a large dimple in space-time, and planets follow the curves around that dimple in their orbits. A black hole creates an infinitely deep well in space-time, a depression so steep that its sides become vertical. Once something falls past a certain point, the slope becomes too steep to climb back out. The mathematics of curved space-time involves concepts that go beyond simple analogies. Einstein's field equations relate the curvature of space-time at each point to the distribution of mass and energy at that point. The equations are elegant but complex, involving tensors that describe how space and time curve in multiple directions simultaneously. Near a black hole, these curvatures become extreme. Space doesn't just curve gently like rolling hills, it curves sharply, like a funnel that gets steeper and steeper until it becomes vertical at the event horizon. Time also curves, its flow changing with position in the gravitational field. Understanding these equations precisely requires advanced mathematics, but their physical meaning is clear. Mass tells space-time how to curve. One of the most striking confirmations of space-time curvature came from observing stars near Sagittarius A star. Astronomers tracked a star called S2, which orbits the supermassive black hole every 16 years in a highly elliptical orbit. At its closest approach, S2 passes within about 11 billion miles of the black hole, traveling at roughly 3% of light speed. Observations in 2018 detected gravitational redshift in S2's light, exactly as predicted by general relativity. As the star climbed out of the deep gravitational well near closest approach, its light stretched to longer wavelengths, appearing redder. This observation directly confirmed that time flows differently in strong gravitational fields, precisely as Einstein predicted. Another star near Sagittarius, a star designated S4714, follows an even more extreme orbit. At its closest approach, this star passes within about 8 billion miles of the black hole, experiencing the strongest gravitational effects we've measured around Sagittarius A star. At closest approach, S4714 reaches about 10% of light speed, experiencing intense gravitational effects. These stellar orbits provide natural laboratories for testing general relativity in strong gravitational fields. Each close passage offers scientists a chance to measure how gravity affects motion, light, and time near a supermassive black hole. So far, every observation matches Einstein's predictions with remarkable precision. The curvature of spacetime is not just theoretical, it's measurable and real. The Event Horizon Telescope's first image of a black hole, released in 2019, showed M87 star, the supermassive black hole at the center of galaxy M87. This black hole contains about 6.5 billion solar masses. The image revealed a bright ring of light surrounding a dark central region, the black hole's shadow. This shadow appears larger than the event horizon itself because light paths bend dramatically near the black hole. Photons passing close get deflected by curved spacetime, creating a dark region roughly 2.5 times larger than the actual horizon. A beautiful demonstration of light bending through warped space. The bright ring comes from light emitted by the accretion disk, bent into our view by spacetime curvature. The 2022 image of Sagittarius A star revealed similar features, but was harder to capture. M87 star is much larger and changes slowly, giving astronomers time to collect data. Sagittarius A star, though much closer to us, is much smaller and changes rapidly. The hot gas around it completes an orbit in just minutes. Capturing its image required sophisticated algorithms to piece together data from multiple telescopes taken simultaneously across the globe. The resulting image showed a bright ring tilted relative to our view, with brighter regions corresponding to gas moving toward us and dimmer regions where gas moves away. The image confirmed that our galaxy's central black hole looks and behaves as theory predicts. These images don't show the black holes themselves. Nothing escapes from inside the event horizon, so black holes emit no light. Instead, we see the silhouette of the event horizon against the glowing accretion disk behind it. The shadow's size and shape encode information about the black hole's mass, spin, and the geometry of spacetime around it. By comparing observations with theoretical predictions, scientists confirm that the shadow matches what Einstein's equations predict. This is remarkable. Equations written over a century ago, based on abstract geometric principles, accurately describe the appearance of objects billions of light years away, where gravity becomes so intense that spacetime curves back on itself. Black holes can spin, and their rotation drags spacetime along with them. This effect, called frame dragging or the lens-Thirring effect, occurs because spinning mass creates a different spacetime geometry than non-spinning mass. Imagine stirring honey with a spoon. The honey near the spoon gets dragged along, swirling around the rotating object. Similarly, a spinning black hole drags spacetime itself into rotation around it. This creates an ergosphere, a region outside the event horizon where spacetime is being dragged faster than light speed. Nothing in the ergosphere can remain stationary relative to distant space. Everything must co-rotate with the black hole to some degree. The fabric of space itself is spinning. The fastest spinning black holes rotate at nearly the theoretical maximum speed. At this limit, the event horizon shrinks to its minimum possible size for the black hole's mass, and the ergosphere extends far outward. Material in the ergosphere can extract rotational energy from the black hole through a process called the Penrose process, named after physicist Roger Penrose. A particle falling into the ergosphere can split into two, with one fragment falling into the black hole while the other escapes with more energy than the original particle had. The energy comes from the black hole's rotation. The infalling particle actually has negative energy from the black hole's perspective, slowing its spin slightly. Recent observations suggest that most supermassive black holes spin rapidly. The jets we observe from active galaxies provide indirect evidence of rotation. These jets seem to require the combination of spin and magnetic fields to form. The James Webb Space Telescope has observed jets from supermassive black holes in the early universe, indicating that even these ancient black holes were spinning. Spin affects the inner edge of the accretion disk, with faster spinning black holes allowing material to orbit closer to the event horizon before plunging in. This creates hotter, brighter accretion disks around rapidly spinning black holes. The rotation rate encodes history, how the black hole formed, and how it has consumed matter over cosmic time. Gravitational time dilation becomes extreme near the event horizon. If you could hover just outside the horizon of a stellar mass black hole while your friend stayed far away, time would pass very differently for each of you. What feels like 1 hour to you might be years or decades for your friend. If you sent a signal once per second by your clock, your friend would receive those signals progressively slower and slower, stretched out over longer and longer intervals as you approached the horizon. This isn't an illusion or an observational trick. Time genuinely flows at different rates in different gravitational fields. Clocks deep in a gravitational well tick more slowly than clocks far away. This time, dilation has practical implications even on Earth. GPS satellites orbit about 12,000 miles above Earth's surface, where gravity is weaker and time runs slightly faster than on the ground, about 45 microseconds per day faster. If GPS systems didn't account for this relativistic time dilation, position errors would accumulate at about 6 miles per day. Every time you use GPS navigation, you're relying on corrections for relativistic time dilation. Near a black hole, these effects become enormously amplified. Time doesn't just run slightly faster or slower. It can differ by factors of thousands or millions, depending on how close you are to the event horizon. Spacetime curvature is not abstract theory. The bending of light paths creates gravitational lensing, which has become a powerful astronomical tool. When light from a distant galaxy passes near a massive object like a black hole or a cluster of galaxies, the light paths bend, magnifying and distorting the background galaxy's image. Sometimes this creates multiple images of the same object or stretches it into arcs and rings called Einstein rings. In 2021, astronomers used gravitational lensing to study a black hole in a distant galaxy, measuring its mass through how it bent light from even more distant stars. This technique lets us study black holes billions of light years away, using spacetime curvature itself as a cosmic magnifying glass. Some of the universe's most remarkable phenomena unfold quietly in the curved spacetime near black holes. Tidal forces near the event horizon can tear apart stars that wander too close, creating spectacular tidal disruption events. As the star stretches into a long stream of gas, some material falls into the black hole, while some gets flung away at high speeds. The infalling material heats up tremendously, glowing brilliantly in X-rays for months or years. Astronomers have observed dozens of these events, each providing insight into how matter behaves in extreme space-time curvature. The violence of these disruptions demonstrates the immense stresses that curved space-time can impose on ordinary matter. We've now seen this bending directly in stellar orbits, gravitational waves, and telescope images of their shadows. Evidence from multiple sources builds a comprehensive picture. Black holes bend space-time so severely that they create measurable effects across vast distances. Time slows near them. Light curves around them. Matter accelerates to relativistic speeds. Space-time itself rotates with them. These are not subtle effects requiring sensitive instruments to detect. They're dramatic transformations of the fundamental structure of reality. We've moved from Einstein's abstract equations to concrete observations of objects that bend space and time more extremely than anything else in nature. The question is no longer whether black holes bend space-time, but how deeply and completely they transform it. You're still here, still awake, still drifting with us through these stories. Take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. Inside the event horizon, space-time becomes so warped that the roles of space and time actually reverse. Outside the horizon, you can move freely in any spatial direction, but must move forward in time. Inside the horizon, the singularity lies in your future, the same way tomorrow lies ahead. Not as a place you might avoid, but as a time that will inevitably come. All paths through space inside the event horizon lead to the singularity, just as all paths through time outside lead to the future. This reversal is not metaphorical. The mathematics of space-time curvature shows that time-like and space-like directions swap. The singularity is when you'll arrive, not where. This means that falling into a black hole is fundamentally different from any other journey. When you travel to a distant city, you can always turn around. When you fall into a black hole past the event horizon, you cannot turn around because the way out is not back through space, it's backward through time, which is impossible. The singularity lies in your inevitable future. You could no more avoid reaching it than you could avoid experiencing tomorrow. This strange property of black hole interiors shows how thoroughly curved space-time can transform familiar concepts. Inside the horizon, space and time exchange their characters completely, creating a region unlike anywhere else in the universe. Tidal forces near black holes can be extraordinary. Tidal forces arise because gravity weakens with distance. So, the part of an object closest to a massive body experiences stronger gravity than the far side. Near Earth, tidal forces from the moon are gentle enough to raise ocean tides. Near a stellar mass black hole, tidal forces become lethal. As you fell, feet first, toward the event horizon, your feet would experience much stronger gravity than your head. This difference would stretch you vertically while compressing you horizontally, a process physicists call spaghettification for stellar mass black holes. This stretching would rip you apart long before you reach the horizon. Interestingly, supermassive black holes have gentler tidal forces at their event horizons. The tidal force depends not just on the gravitational field strength, but on how rapidly it changes over distance. Larger black holes have larger event horizons, and gravity changes more gradually across that larger distance. If you fell into a supermassive black hole like Sagittarius A star, you could cross the event horizon without being torn apart. You wouldn't feel anything particularly special at the moment of crossing. Only later, as you continued falling toward the singularity and tidal forces grew stronger, would the stretching become extreme. Size matters in unexpected ways when it comes to spacetime curvature. From your perspective, falling into a black hole, the experience would be surreal. Looking outward, you'd see the entire future history of the universe compressed into your final moments. Light from stars and galaxies would be blue shifted to higher energies, compressed by time dilation. The universe outside would seem to speed up, aging billions of years in what feels to you like seconds or minutes. Meanwhile, looking toward the singularity, you'd see increasing darkness and distortion as light paths bend impossibly around you. Space itself would seem to collapse inward. This journey would be utterly unique. Nothing else in the universe offers such an extreme transformation of perspective. Black holes might connect to other regions of spacetime through structures called wormholes. These are theoretical tunnels through spacetime, connecting distant locations or even different universes. Einstein's equations allow wormhole solutions, though making them stable and traversable requires exotic matter with negative mass-energy density, which may not exist. Some scientists speculate that black hole singularities might connect through wormholes to white holes, time-reversed versions of black holes that expel matter instead of consuming it. But no evidence supports this speculation. Even if wormholes exist, crossing through them would likely be impossible or fatal. Still, the mathematics of curved spacetime permits these fascinating possibilities. The interior geometry of a black hole might be far stranger than a simple funnel to a singularity. Some solutions to Einstein's equations suggest black holes could have the complex internal structures. Rotating black holes described by the Kerr metric might have an inner event horizon and a ring singularity rather than a point singularity. The mathematics even suggests you could pass through the ring and emerge into a different region of spacetime. But these features probably aren't physically real. Quantum effects, which our classical equations ignore, likely modify the structure dramatically. The interior remains purely theoretical, since no information can escape to tell us what conditions are actually like inside. Recent theoretical work suggests the event horizon might have more structure than previously thought. The black hole information paradox has led physicists to propose that the horizon contains quantum information encoded in subtle correlations between Hawking radiation particles. Some theories suggest the horizon is covered in a fuzzball of quantum strings rather than being a smooth surface. Others propose firewalls, regions of intense energy at the horizon that would incinerate anything crossing. These ideas attempt to resolve contradictions between quantum mechanics and general relativity. While we can't test them directly, they reveal how deeply black holes challenge our understanding of spacetime's fundamental nature. The relationship between black holes and entropy suggests deep connections between spacetime geometry and information theory. Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to their event horizon surface area, not their volume. This seems strange. Normally, the entropy of an object depends on its volume, on how many ways particles inside could be arranged. But black holes are different. All their entropy is encoded on their surface. This led to the holographic principle, which suggests that all the information in a three-dimensional region can be encoded on its two-dimensional boundary. Black holes hint that spacetime itself might be a hologram, with reality's true information stored on distant surfaces. Halfway through our journey, the answer is becoming clearer. Black holes bend space and time through their mass, creating extreme curvature in the spacetime fabric. This curvature is so severe that it creates an event horizon, a boundary where spacetime curves back on itself, where time slows to infinity from an outside perspective, where space and time swap roles. The curvature creates gravitational time dilation, bends light paths into rings and shadows, generates tidal forces that tear objects apart, and possibly encodes information in quantum structures we're only beginning to understand. Yet these extreme effects all follow from one elegant principle. Mass curves spacetime, and curved spacetime tells matter how to move. Let each breath guide you to realize time is yours, a separate stream that only you are living, while the vast universe continues to spin, expand, change. This second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe, and we continue drifting. We now understand that black holes are not cosmic vacuum cleaners but natural consequences of how gravity works. When mass concentrates sufficiently in a small region, spacetime curvature becomes self-reinforcing. The curvature creates stronger gravity, which increases curvature further, in a feedback loop that continues until spacetime curves so completely that an event horizon forms. This is not mysterious or magical. It follows inevitably from Einstein's field equations relating mass to spacetime curvature. Every massive object creates some curvature. Most objects, like planets and stars, create gentle curvature. Black holes simply take this process to its natural extreme, concentrating mass so densely that curvature becomes total. The minimum mass for a black hole to remain stable is roughly 3 solar masses. Below this limit, quantum pressure from neutrons can resist gravity, forming neutron stars instead. This mass limit, called the Tolman-Oppenheimer-Volkoff limit, represents the point where gravity finally overwhelms all forms of matter and energy resistance. Above this threshold, nothing can prevent collapse to a black hole. This shows that black holes aren't rare cosmic anomalies. They're a natural state that matter adopts when compressed beyond a certain density. Given enough mass in a small enough space, nature has no choice but to form a black hole. Spacetime curvature near black holes affects not just matter and light but also fundamental forces. The electromagnetic field itself becomes distorted by curved spacetime. Magnetic field lines can be dragged and twisted by the rotating spacetime in the ergosphere, creating complex magnetic field geometries. These fields play crucial roles in launching jets and shaping accretion flows. Even the quantum vacuum responds to curved spacetime, with particle creation rates depending on local curvature. Everything that exists in spacetime, particles, fields, forces, must conform to the geometry that mass creates. Black holes demonstrate that spacetime is not just a stage, but an active participant. The study of black holes has revealed that general relativity works remarkably well even in extreme conditions. Every prediction, time dilation, gravitational lensing, event horizon size, black hole shadows, gravitational waves, has been confirmed through observations. This success is extraordinary because Einstein developed general relativity using weak field approximations, studying gentle spacetime curvature around the Sun and Earth. Yet his equations work perfectly when curvature becomes extreme, when spacetime folds into event horizons and singularities. This suggests that general relativity captures something deeply true about how reality works. The mathematics isn't just convenient. It describes actual spacetime geometry. Black holes teach us that spacetime has physical properties like any other substance. It can be compressed, stretched, rippled, and rotated. It carries energy. Gravitational waves transport energy across the universe. It has rigidity. Passing gravitational waves make it oscillate at characteristic frequencies. It can even be torn or cut in quantum foam at the smallest scales. Spacetime is not abstract geometric backdrop, but a dynamic physical entity. This realization transforms how we think about reality. Space and time aren't containers that hold the universe. They're woven into the universe itself, shaped by what exists within them. The James Webb Space Telescope has observed jets from supermassive black holes in galaxies less than 1 billion years after the Big Bang. These jets extend for millions of light years, pumping enormous energy into their surroundings. The early appearance of these structures suggests that supermassive black holes and their extreme spacetime curvature have influenced galaxy formation throughout cosmic history. Black holes might help regulate star formation by heating gas and preventing it from cooling and forming stars too rapidly. The most massive objects that bend spacetime most extremely may have shaped the evolution of galaxies across billions of years. Merging black holes create the strongest gravitational waves in the universe. When two black holes spiral together, they convert up to 5% of their combined mass into gravitational wave energy in the final seconds before merger. This is an extraordinary energy conversion, far more efficient than nuclear fusion, which converts less than 1% of mass to energy. The merging black holes literally shake spacetime, sending ripples outward at light speed. These ripples carry information about the merger, allowing us to reconstruct the masses and spins of the original black holes purely from the gravitational wave signal. The detection of gravitational waves has confirmed another prediction. Black holes ring like bells after merging. When two black holes collide and merge, the resulting larger black hole is initially distorted, not perfectly spherical. This distortion creates oscillations in the event horizon shape, which radiate gravitational waves at specific frequencies called quasi-normal modes. These frequencies depend only on the final black hole's mass and spin. By measuring these ring-down frequencies, Scientists can test whether the merged object is truly a black hole as predicted by general relativity. So far, every measurement matches theoretical predictions perfectly. The existence of intermediate mass black holes remains somewhat mysterious. These objects, with masses between hundreds and thousands of suns, are harder to detect than their smaller or larger cousins. Some may form from runaway collisions in dense star clusters, where stars merge repeatedly until they create a black hole massive enough to continue growing by absorbing other stars. Others might form from the direct collapse of massive primordial gas clouds. Recent gravitational wave detections have found several mergers producing intermediate mass black holes, confirming that this population exists and helping scientists understand how supermassive black holes might have formed. The growth rate of black holes has theoretical limits. The Eddington limit describes the maximum luminosity an accreting object can achieve before radiation pressure pushes away in-falling matter. This creates a natural speed limit for growth. Under ideal Eddington limited conditions, black holes can roughly double their mass every 45 million years, following a gentle exponential curve governed by the balance between gravity and radiation. For a black hole to grow, material must fall in, but falling material heats up and radiates. If radiation becomes too intense, it blows away additional material, limiting accretion. Yet we observe supermassive black holes in the early universe that must have grown faster. Some scientists propose that primordial black holes formed in the early universe, long before stars existed. Density fluctuations in the first moments after the Big Bang might have created regions dense enough to collapse directly into black holes. These primordial black holes could range from tiny masses smaller than asteroids to thousands of solar masses. Some might even account for part of the dark matter we observe through gravitational effects but cannot see directly. While purely speculative, this idea suggests that black holes might be as old as the universe itself, bending space-time since the earliest moments. Black holes might be surprisingly common. Current estimates suggest our galaxy contains about 100 million stellar mass black holes, formed from the deaths of massive stars over billions of years. Most are invisible, floating alone through space with no accretion disk or companion star to reveal their presence. Only when they consume matter or merge with another compact object do we detect them. This hidden population of black holes means that curved spacetime of extreme degree exists throughout the galaxy, in countless isolated pockets scattered among the stars, quietly warping space and time in their immediate neighborhoods. The rotation of black holes has fascinated physicists since Roy Kerr discovered the mathematical solution for rotating black holes in 1963. Unlike non-rotating Schwarzschild black holes, which are perfectly spherical, rotating Kerr black holes are flattened at their poles due to centrifugal effects. The faster they spin, the more oblate they become. At maximum rotation, the event horizon shrinks to its minimum size and the ergosphere extends far outward. This rotation rate limit exists because adding more angular momentum to a maximally spinning black hole would require the event horizon to shrink below a critical size, which is impossible. Frame dragging around rotating black holes creates bizarre effects. If you tried to orbit a spinning black hole in the opposite direction to its rotation, you'd find it impossible to remain stationary relative to distant stars. space-time itself is rotating, dragging you along. You could orbit more slowly than you'd expect, carried partly by the rotating space-time, or you could fight against the drag, but you couldn't stand still. This shows that rotation is not just a property of the black hole's matter, but a property of the space-time geometry itself. The fabric of reality spins. The mechanism is now clear. Mass curves space-time, and sufficient mass curves it completely. Each stellar mass black hole carries with it a region of intensely warped space-time, a bubble of curved reality drifting through the cosmos. Where two black holes orbit each other, their space-time curvatures interact, creating patterns of interference and reinforcement. When they merge, these bubbles combine, briefly creating chaotic ripples that propagate outward as gravitational waves. The galaxy is not filled with uniform, flat space-time, but with countless dimples, wells, and warps, each one a local distortion in the fabric of space and time. Black holes demonstrate that gravity is not a force in the traditional sense, but a manifestation of geometry. Other forces, electromagnetism, the strong and weak nuclear forces, are true forces, mediated by particles that carry them. But gravity is different. It emerges from space-time curvature itself. Objects in free fall feel no gravitational force. Astronauts in orbit feel weightless because they're following the natural curves of space-time around Earth. Only when something prevents you from following those curves, like the ground pushing up against you, do you feel weight. Gravity is geometry made manifest. The concept of escape velocity helps us understand event horizons. Escape velocity is the speed needed to escape from a gravitational field without further propulsion. Earth's escape velocity is about 7 miles per second. The Sun's escape velocity at its surface is about 380 miles per second. For a black hole, escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, nothing can escape. The event horizon is simply the surface where escape velocity reaches light speed. Closer than this boundary, escape is impossible, not because something holds you back, but because the required speed exceeds the universe's speed limit. Temperature and black holes have an inverse relationship. Hawking showed that smaller black holes are hotter. They emit Hawking radiation at higher temperatures. A stellar mass black hole of 10 solar masses has a Hawking temperature of about 6 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation filling space. It actually absorbs more radiation than it emits. But a microscopic black hole would be extremely hot, radiating intensely. If primordial black holes exist with masses smaller than asteroids, they should be evaporating rapidly, perhaps even explosively. This inverse temperature-mass relationship is purely quantum mechanical, with no classical analog. The no-hair theorem states that black holes are remarkably simple objects, characterized by just 3 properties: mass, electric charge, and angular momentum. All other information about what fell into the black hole, its composition, structure, history, disappears behind the event horizon. 2 black holes with identical mass, charge, and spin are completely indistinguishable, regardless of whether they formed from stars, gas clouds, or exotic matter. This simplicity is striking. despite the complex processes that form black holes, the end result is one of the simplest objects in physics, described completely by 3 numbers. Recent theoretical work suggests the no-hair theorem might not be completely accurate. Quantum effects might allow black holes to have additional subtle properties. Quantum hair that distinguishes them beyond just mass, charge, and spin. This quantum information might be encoded in subtle correlations in the Hawking radiation or in the quantum state of the event horizon itself. If true, this would help resolve the information paradox by allowing information to escape from black holes gradually through Hawking radiation. But these ideas remain highly speculative, requiring a complete theory of quantum gravity to fully understand. Black holes teach us that extreme space-time curvature doesn't require extreme mass, only extreme density. You could theoretically make a black hole from anything, even water or air, if you compressed it enough. The Schwarzschild radius defines the critical size. Compress any mass into a sphere smaller than its Schwarzschild radius, and it becomes a black hole. For Earth, this radius is about 1 centimeter. For the Sun, it's about 3 kilometers. Both objects are far larger than their Schwarzschild radii, so they're not black holes. But the principle is universal. Sufficient density creates an event horizon. The universe itself might have a kind of event horizon called the cosmological horizon. Due to cosmic expansion, distant galaxies are receding from us faster than light. Light they emit now will never reach us. They're beyond our cosmological horizon. This isn't quite the same as a black hole's event horizon, but it's conceptually similar. A boundary beyond which no information can pass. In this sense, we all live inside a kind of horizon, able to interact only with the portion of the universe close enough that light can traverse the expanding space between us and it. The relationship between black holes and the laws of thermodynamics suggests deep connections we're still exploring. Black holes obey all 4 laws of thermodynamics if we interpret their event horizon area as entropy and their surface gravity as temperature. They absorb matter, increasing their entropy. They cannot spontaneously split into smaller black holes, preserving the second law. When 2 black holes merge, their combined surface area always exceeds the sum of their original areas. These parallels hint that thermodynamics is not just about statistical mechanics of particles, but something more fundamental about information and space-time geometry. Observing black holes across cosmic time reveals how these objects have shaped the universe. Early black holes in dwarf galaxies might have prevented those galaxies from growing larger by heating gas and preventing star formation. In larger galaxies, supermassive black holes and their jets create enormous bubbles of hot gas that can extend beyond the visible galaxy. These bubbles affect star formation rates, chemical enrichment, and galaxy evolution. Black holes, through their extreme space-time curvature and the energetic processes it enables, have influenced cosmic structure from the smallest scales to the largest. Black holes have taught us that our understanding of space and time was incomplete. Einstein showed that space and time are not separate, that mass curves their combined fabric, and that gravity emerges from this curvature. Black holes proved these ideas correct by existing exactly as the equations predicted. They bend space and time so completely that they create event horizons, regions from which nothing escapes. They demonstrate that spacetime is not just mathematics, but physical reality, shaped by mass and energy. This understanding transforms how we see the universe and our place within its curved geometry. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath, inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits, unhurried, unresisting, simply existing. We're almost there now. Black holes remind us that the universe is stranger than our intuition suggests. We evolved to understand falling rocks and moving predators, not curved spacetime and event horizons. Yet mathematics and observation reveal reality far beyond everyday experience. Space can curve. Time can slow. Horizons can form. These aren't philosophical concepts but physical facts, confirmed by gravitational waves, bent light, and black hole shadows. Our intuition misleads us. Reality operates on principles we never encounter in daily life. This is humbling and wonderful. The universe is deeper than we imagined. The mathematics of curved spacetime is beautiful. Einstein's field equations relate geometry to matter with elegant simplicity. 10 coupled differential equations describe how mass curves spacetime and how that curvature affects motion. From these equations flow all predictions about black holes, event horizons, time dilation, gravitational waves, everything. The equations are compact, symmetric, beautiful. That such complex phenomena emerge from such simple mathematical relationships suggests something profound. The universe operates on principles of deep mathematical harmony. Physicists seek a theory of quantum gravity that would describe spacetime at the smallest scales. General relativity works beautifully for large-scale phenomena, but breaks down at singularities where quantum effects dominate. String theory, loop quantum gravity, and other approaches try to merge quantum mechanics with spacetime geometry. We don't yet know which approach is correct, but the quest itself reveals something important. Space and time might not be fundamental, but emergent properties. Arising from deeper quantum structures we're still discovering. Black holes might be cosmic recycling centers, hawking radiation, though unimaginably slow for large black holes, means that over vast timescales, all black holes eventually evaporate. The mass that fell in gets returned to the universe as radiation. Information might be preserved in subtle quantum correlations. If so, black holes don't destroy information, they transform it, mixing it thoroughly before releasing it back. Nothing is truly lost, only changed beyond recognition. The study of black holes connects many fields: astronomy, particle physics, quantum mechanics, thermodynamics, information theory. These objects sit at intersections between different areas of physics, forcing us to think about how these areas relate. They're natural laboratories where quantum mechanics meets gravity, where thermodynamics meets cosmology. Understanding black holes fully might require a unified theory. a framework that connects all physics. They're signposts pointing toward deeper understanding. Ancient astronomers watched stars move across the sky and wondered about the heavens. They had no concept of curved spacetime or event horizons. Yet they asked fundamental questions. What are stars? Why do they move? What is the nature of space? We continue that tradition, using modern tools to explore the same ancient wonder. The questions evolve, but the curiosity remains constant across millennia. Black holes teach patience. Their formation takes millions of years. Their evaporation takes longer than the current age of the universe. Signals from their mergers travel for billions of years before reaching us. They exist on timescales that dwarf human lifespans. Yet we've learned to observe them, to measure them, to understand them. This shows human persistence. We can comprehend phenomena operating on scales vastly different from our own. Every black hole in the universe is slightly different. Each has its own mass and spin, its own history. Some consumes matter actively, while others drift quietly through space. Some merge with companions, while others remain isolated. Yet, all follow the same physical laws, described by the same equations. This unity in diversity is characteristic of nature, individual variation within universal principles. The darkness at the center of a black hole is absolute. No light escapes, no signals emerge. Yet this darkness reveals truth. By observing what we cannot see, by measuring shadows and absences, we learn about reality's structure. Sometimes truth comes from noticing what isn't there, from the shapes of silence and darkness. Spacetime near black holes challenges language itself. Words like inside and outside lose clear meaning when space and time exchange roles. Phrases like position in space become ambiguous. Our language evolved for everyday experience, not for regions where time becomes spatial and space becomes temporal. Sometimes mathematics expresses truths that words cannot capture. The answer to our question is becoming clear. Black holes bend space and time by concentrating mass so intensely that space-time curves back on itself, creating event horizons where time slows infinitely and escape becomes impossible. This bending is not metaphorical but literal, measured and confirmed through multiple observations. This bending affects everything near them. Light curves into spirals and rings. Time flows at different rates depending on distance. Matter accelerates to light speed before crossing the horizon. Even space itself rotates with spinning black holes. All these effects follow from space-time curvature, from geometry responding to concentrated mass. Yet the deeper answer is that black holes change how we understand reality itself. They show that space and time are not fixed containers but flexible fabric, woven together and shaped by mass. They prove that extreme conditions can create structures beyond our intuition. Following mathematical laws we've learned to read. They teach us that the universe operates on principles we had to discover through careful thought and observation. No human ever experienced an event horizon directly. Yet we predicted them through mathematics and found them through astronomy. This shows the power of reason and observation working together. So, could black holes bend space and time? They already have. They've been bending space-time since the first massive stars died billions of years ago. They bend it now in countless locations throughout every galaxy. The bending is ongoing, constant, fundamental to how the universe works. The real question is what this means for us, here, far from any black hole. It means that space and time are not what we thought. It means that reality follows laws stranger than common sense suggests. It means that mass and energy shape the very stage on which events unfold. It means that even empty space has structure and properties. It can vibrate with gravitational waves, curve under mass, spin with rotating objects. Space is not nothing. It's something, a dynamic fabric woven throughout the universe. Time is not an independent flow, but part of that fabric. This understanding connects us to the cosmos. The gentle curvature of spacetime around Earth keeps us in orbit around the Sun. The extreme curvature inside black holes follows the same principles. We live within curved spacetime, shaped by all the mass around us. Earth, Sun, galaxy, universe. Every moment you experience occurs within the curved spacetime created by Earth's mass. Your position right now is a position in four-dimensional spacetime, not just three-dimensional space. You're traveling through time at 1 second per second, following the curves that mass creates around you. Black holes are the extreme case, but the principle is universal. All mass curves spacetime. Stars curve it significantly. Planets curve it gently. Even your own body curves spacetime slightly around you. The curvature is tiny, unmeasurable, but real. You participate in shaping the universe. Understanding this can change how you see yourself in the cosmos. You're not a separate observer watching the universe from outside. You're part of the universe. Your mass contributing to spacetime's geometry. Your motion following curves created by all other masses. You and the universe are woven together inseparably. Black holes reveal this principle by taking curvature to its natural extreme, bending spacetime so completely that event horizons form. They bend spacetime so completely that event horizons form, creating regions from which nothing escapes. This dramatic example helps us see the gentler curvatures everywhere. They illuminate the principle by demonstrating its most extreme expression. The universe is built on relationships between mass, energy, space, and time. These aren't separate things, but aspects of a single reality. Mass and energy tell spacetime how to curve. Curved spacetime tells mass and energy how to move. Everything affects everything else in an eternal dance. This interconnection is beautiful. No part of the universe exists in isolation. Everything influences and is influenced by everything else, through gravity, through curved spacetime, through fields and forces that permeate existence. We're all connected through the fabric of spacetime, through curves and warps that extend across the cosmos. So, yes, black holes bend space and time profoundly, but more importantly, they taught us that space and time can be bent, that reality is flexible geometry, that we live within a universe more beautiful and strange than we imagined. This is the gift of understanding, seeing reality more clearly. And so, our quiet journey through black holes and space-time comes to a gentle close. We've traveled from Einstein's revolutionary ideas about curved reality to the shadows of supermassive black holes seen by telescopes spanning our planet. discovering along the way that space and time are woven together into flexible fabric. From event horizons where time stops to gravitational waves rippling across the cosmos, we've glimpsed how black holes are both impossibly strange and perfectly natural. Black holes remind us that the universe is both knowable and mysterious. Much of reality's deepest structure happens in silence, in curved spacetime invisible to the eye, in mathematical relationships between mass and geometry. They teach us humility and wonder. Without curiosity and careful observation, we never would have known that space and time could bend. By pausing to notice, we glimpse the extraordinary hidden within cosmic darkness. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in a black hole, where all boundaries dissolve. Light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the quiet stillness pulling you toward sleep. Prepare for deep sleep. No boundaries left. Only peace. If this gentle journey through the cosmos brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now, nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of black holes and space-time to fade now, like starlight dimming at dawn, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gentle gravity is pulling you down into soft comfort, into rest. If sleep comes, let it carry you like a leaf floating on a still pond, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, black holes will still be bending space-time. The universe will still be following Einstein's equations. But tonight belongs to stillness. Rest well, peaceful traveler. And remember, you exist within curved space-time, part of the cosmos, connected to everything through invisible geometry. Fall asleep to gentle facts. Dream deeper with bedtime science. Good night.